All right. Escape velocity. Technically, I guess escape speed is more accurate because we're talking about energy, and there really is no need to worry about directions as such. But there is a direction associated with escape velocity, and of course it would be straight up or straight away from the object that you were dealing with. So what does this mean? Well, let's first go back to our picture of how we drew energy or described gravitational energy as a stretched out dent in the rubber sheet of space-time, remember? And we said that if there was a body like Earth situated here, at the center of Earth, right at the bottom of the well, we said that the amount of gravitational energy is negative. That's why in the formula, it's negative G m1 m2 over r. And so if you add energy to a negative number, if you add energy, you will climb up out of the well, just like on an axis. If you're down here at a negative number and you add to it, well, it'll pull you up towards zero. And so at the very top, we have zero EG. Or I guess a better way to write that is EG equals zero. So here's an interesting thing. EG would be zero. Now, I just realized that when I was talking to you earlier, I said that EG could be zero at the center of the Earth. It wouldn't actually be zero, it would be infinitely large, wouldn't it? I said that backwards. If you were to possibly get to the center, the gravitational energy at a point in space can grow to infinity. But it's impossible to get to a point in space. So I just realized as we're talking, EG0 would be here, way far away from the Earth, and you would have to input. All of this could be considered the kinetic energy that you have added to yourself to get you to move up Earth's energy well and get out. All right? So we're going to use that fact to figure out what the velocity you would need. What speed would give you enough kinetic energy to allow you to reach a height where you have climbed completely out of Earth's gravity well, and you are now resting here, completely not moving, but not rolling back in. And of course, at that point, that would be when your EG has reached all the way up to zero from the negative number that it once was. Okay, so let's write our expressions. Once again, we always start with our good old conservation of energy. The total mechanical energy at any position 1 must be equal to the total mechanical energy at any other position 2. All right? Now, if I go back to my picture, and maybe if I just erase some of these things that I've drawn in here, because it looks a little bit crazy. Let's take this out as well. All right. Now, where are we going to start? Our position 1 will be at the surface of the Earth, because that's where we are. We want to escape from Earth's surface. So there's our position 1. And what would we have at that position? Well, we would have EG because we are 1 Earth radius away from the center, right? And we would also have a tremendous amount of EK that we're going to have to get. That's kind of what we're after. We want to know the speed associated with this kinetic energy that's going to be able to get us out of the well. So somebody's going to have to kick us really hard, right? Give us some kind of energy to make us move. Position 2 then would be once we escape the well up here and we've reached a level where we will no longer fall back in. But the minimum amount of kinetic energy that we need to do that would be just the right amount to get us right to the top of the hill without moving after that. So guess what? At this position, we'll have lots of EG. There'll be more EG. I'll call this one 1, this one 2. But well, wait a minute now, let's just write this. There'll be EK. Our kinetic energy, though, is going to drop to 0 because we're not moving. And since we've added energy to a negative number, what did we say that EG is out here on the edge? 0 as well. So we have no gravitational energy at this point, because we started off with a large negative number down here, and we added energy until we got to 0. And the energy we added was the kinetic energy, which is now also all used up and 0. So we have 2 zeros in this equation that are going to make this nice and simple for us. All right? So let's go to our equation then and write the Eg at position 1 plus the kinetic energy at position 1 must equal the Eg at position 2 and the kinetic energy at position 2. But we've just finished explaining that for this scenario, Eg2 and Ek2 will both be 0. This is backwards to what we did before. Before, we turned all the kinetic energy into gravity, and we said there should be lots of more Eg. There is more Eg, but we've added that more Eg to the original negative Eg, right? Producing a 0. That's why it seems backwards. Because we started off with a debt, and we added money to the bank, and now we've got no balance, 0. So that's why it seems odd in this sense. So these are both zeros. And then all that's left, well, let me move that because I'll have to write it in the equations. All that's left is to write negative G M1 M2 divided by R. This is Eg1, so it's R1. And then plus the kinetic energy, 1/2 mv squared. And it will equal 0. Let's move that to the other side. 1/2 mv squared equals positive G M1 M2 over the initial R1. And again, this is where your textbook starts. And they throw this in there and they say, look at this. And it's hard to know how they got to that point without seeing the introduction to the story, but now we kind of get it. All right, so let's just look at this for a minute. One of these masses is the same on both sides. This mass is the mass of the object that is trying to escape from the Earth. The object, the soccer ball somebody has kicked, or the rocket that has been launched. And one of these masses is also that same rocket, so they will cancel out, leaving us with 1/2 of v squared equals g mass. This would now become the mass of the Earth, right? And the radius of the Earth is r1 because we were on the surface. The surface is where we want to escape from. If you multiply both sides by 2, you can get v squared equals 2g mass of Earth over radius of Earth. And if you take the square root of both sides, then I'll just kind of bring it over here. You get v, which is the escape velocity that we talked about, and it would be the square root of 2 capital G mass of Earth over radius of Earth. And that formula allows us to figure out the speed you would need to be launched at from Earth's surface in order to not come back down. You would escape out of Earth's gravity. Now, that would be just the bare minimum to get you out. Once you got out, you'd be kind of floating out in space and not really moving anymore. And technically, Earth's gravity is infinite. So we understand that in order to escape from Earth, you'd have to have a slight little bit more than whatever speed this gives you. But it's sort of the limit. It's kind of the in-between number. So we call it the escape velocity. And it's the escape velocity because we set the question up specifically to reflect the energy at those two positions from the Earth's surface and what energy you would have if you did escape from Earth's gravity well. Okay? Now, you can find the escape velocity from anything. This is set up to be Earth. But if you change it to escape velocity to the square root of 2g times the mass of anything at all, that's supposed to be a question mark, which didn't work out very well, the mass of any object that you want to escape from, and you use the radius of that same object that you are escaping from, you can find the escape velocity of anything. If you were out in space, floating, and you don't need a spacesuit because whether you're dead or alive, you still have the same mass. But if there was a tiny flea on top of you, that flea would have a spacesuit on because he's alive and he's going to jump. you could figure out the speed he needed to jump to escape from you and not be pulled back in towards you by your gravity. And you would do that by using the mass of you and the radius of where the fluid is standing to your center of mass, which might be, 10 centimeters or something, if it's on your scale. So you can find the escape velocity from anything. Typically, though, we use it to define the escape velocity from planets like Earth, or the moon, if you want to land on the moon. When we land on Mars, if we want to take a rocket and come back home, we'll need to know how to escape from Mars's gravity. So we could use the mass of Mars and the radius to Mars's surface to figure out the escape velocity of Mars. And so it's a simple little equation. All right. The other equation that we can figure out has to do with orbiting around an object instead of escaping from it. So first we have to talk about what an orbit actually is. So here is an object, say the Earth. And what I'm going to imagine is that I'm going to fire a gun. Let's use nice purple. We haven't used purple in a while. If I shoot a bullet sideways on Earth, it will go sideways, but eventually it will fall down and crash with the Earth, right? Because gravity is pulling it down. If I shoot that bullet faster horizontally, it'll make a bigger curve, but it'll still eventually crash with the Earth. If I shoot it faster, it'll curve around, but eventually crash with the Earth. If I shoot it really fast, faster than Earth's escape velocity, it will shoot off into space and never come back. Somewhere in between, there's a magic speed. If I shoot it at just the right speed, it will fall, being pulled towards Earth's center by the centripetal force of gravity. But as it's falling, Earth itself is curving away. So it's kind of like a dog chasing its tail. The object is trying to fall to the surface, but the surface keeps falling away. And the object will fall indefinitely around the Earth and around the Earth, trying to catch the tail. Right? But the curvature of this purple orbit and the curvature of the Earth's surface match each other. And the two continuously fall away. What this means is when you are in orbit, you are not floating, standing still. You are moving very fast around the Earth, so fast that as you fall, Earth falls away from you, and you just keep falling around it. So an orbit is technically falling around a planet. It's not like on TV where it looks like everybody's staying still. The space shuttle doesn't float in space. It falls around Earth at a very high speed. And that's what we're going to figure out. We're going to figure out what speed you would need. Now, of course, if we look at the purple line, it's a circle. And we've learned already that circles and speeds are related to the centripetal force that pulls you in. So we can use centripetal force as our idea here. Now notice how we're not using energy equations. What we're going to say is that the net force on this object is equal to the force of gravity pulling it down towards the Earth, right? The object going around. But because it's moving in a circle, if we want that purple circle to appear and not have one of the other lines, it's not a circle, then the net force has to be centripetal for circular motion. So let's continue this. mv squared over r is how you calculate centripetal force. And the force of gravity between two objects when they're far away, we're not going to use mg because we're talking about being far away, g m1 m2 over r squared. So pay attention. This is force, not energy. Remember how I said it's easy to confuse those two equations? We're using the force one here. But if we look at it, we can see that the mass of the object that's orbiting around is the same as one of these masses, so that cancels out. And we're left with v squared over r equals g m, and the mass left is the mass of Earth now, over r squared. Right? If I multiply both sides by r, I can get v squared equals g mass of Earth divided by r. And if I take the square root, then the velocity is root g mass of Earth divided by r. R is the height of the orbit. Now, height of orbit above the center of the Earth. Remember, we're always talking about the center of the Earth, not above the surface. Height above the center. And v is the speed that you would need. We call it the orbital speed. It's the speed you would need to make that orbit work. In other words, to make it a nice circle that goes around the world with exactly the same shape as the Earth's curvature. Meaning you would fall to Earth but never land. And you would fall around completely. Now notice how closely that is related to the other expression that we did before. The only difference is this little 2 here. So these are also easy to confuse. So let me just write them together so you can see them. In green, we did the escape velocity or escape speed, which is how much speed you would need to shoot directly away from an object and escape from its gravity. And so v escape was the square root of 2g mass of the object and radius. Whereas orbital speed, which is the speed that you need to fall around an object and maintain an orbit, would be v orbit equals the square root of just g m over r. And the mass is the mass of the object you're orbiting, and the radius is your height above its center. Same thing here, the mass is the mass of the object you're escaping from, and r is the height above its center at which you are trying to escape from. So if you are on the surface of the Earth, that would be the r. But it is possible to escape from a planet. One of the plans is to go to Mars. Well, if we launch a rocket from the surface of Earth, we need a lot of energy because there's a high escape speed. The escape speed works out to be about 11,000 meters per second. If you actually put in the numbers, it's 11,000 meters per second. It's pretty darn fast to launch something to escape Earth. That's how high, if you kick a football 11,000 meters per second, it won't come back down if you kick it straight up. But good luck kicking that, right? But what we can do is we have objects in orbit. We have the International Space Station. We could build platforms in orbit around the Earth, right? Now remember, these objects are moving at very, very high speeds. The orbital speed for a typical space shuttle mission is somewhere around 7,000 meters per second, I think, give or take. So that's fast. The space shuttle, when it looks like it's floating in space, is actually moving at 7,000 meters per second around the Earth. Very fast. That's why it's so dangerous to run into space junk or a piece of rock or something that might be moving in the opposite direction. If somebody leaves a wrench in space from the last repair of the Hubble telescope, that wrench is moving at 7,000 meters per second. And if it happens to be moving in the opposite direction as you, and you're out on a spacewalk, you're going to be dead. Which is why space is so dangerous, right? There's lots of stories I can tell, and I'll tell you one after we're done with the video. Anyway, what we plan to do is bring the components of the rockets up to a platform like the space station, which is much higher, and then launch from here. So your escape speed would be less because your R is much further out. So you could use less kinetic energy and still escape Earth's gravity because you've already gotten this high. You've already gotten to that spot. Anyway, those are all different examples. These are pretty much plug-and-play equations. You plug in the numbers and get the answer, so there's nothing really complicated. And so we'll leave it at that. And I think that's good enough for today.